What's buzzin', cousin? Welcome back. In this video, we're following up with our discussion of general linear systems problem. We're going to look at our second toy example. The reason we're doing toy examples is there's a lot going on in this, and for now, I don't want to get bogged down in modeling details. Very soon, we will actually construct general linear systems problems from real-world models to apply this theory. But in the beginning stages, I want to really focus in on the theoretical structures so that we can partition and chunk knowledge and keep it simple. With that said, let's go on with this toy example. We're looking at a general linear systems problem involving a rectangular matrix. This matrix has 4 rows and 7 columns. Right-hand side vector has 4 rows, so we've got a 4 by 7 times a 7 by 1 equals a 4 by 1. The question is, what are the individual coefficients in this vector x that can be scaled by the columns of A to produce the output of that linear combination, which is given by this vector B? We recall from our previous videos in this lesson, in order to solve the AX equal B linear system, we're going to apply a sequence of elementary matrices to the left-hand side of that equation, group those elementary matrices together and call that a single matrix E. That matrix is invertible. Multiply E on the left of that equation, both on the left-hand side and the right-hand side. E times A, we will continue to transform to reduce A until we get A in row reduced echelon form. Those transformations, when we apply them to B, that final vector we're going to call Y. Once we have U equals E times A, the RREF of A, then we're going to use U to find the complete solution that solves this equivalent linear systems problem. As we saw in lesson 17, it is actually non-trivial. It takes a ton of work to do individual matrix transformations using elementary matrices. Instead, one of the things that we do is use our calculator, online version or TI, doesn't matter, to transform this into RREF. We're going to do that in just a second, but before we do, I wanted to give a formal definition that shows up in many linear algebra classes. An augmented matrix is a matrix formed using the left-hand side coefficient matrix A and the right-hand side vector B. If I have an M by N matrix A and an M by 1 vector B, to form the augmented matrix, I literally just glue B on the end of A. That extends the number of columns in A by 1. So instead of N columns, it has N plus 1 columns. And we call the matrix that we produce the augmented matrix formed by A and B. The reason that augmented matrices are really useful is when we go to use our online calculator, here we're just going to search Octave online. The first thing that comes up is Octave. And let's go ahead and scroll down to the bottom of this. I really don't need to see that, so I'm going to go ahead and clear. We're going to go ahead and save A. I'm going to do it in a way that's a little bit different. First thing I'm going to say is, hey, A is a 4 by 7 matrix. Let's populate it with all zeros. And then in my case, I'm going to do the column partition this time, which is to define A by columns. The first column of A, in colon notation, that's A, open parentheses, colon, comma, 1, close parentheses, is given first entry -2, second entry 2, semicolon, third entry -2, semicolon, fourth entry 2. Nice, when I execute that I see actually the first column of A is populated. We're going to go ahead and do the second column of A and the third column of A. Second column of A is 1 in the first entry, semicolon, -1, semicolon, 1, semicolon, -1. I'm going to go ahead and put a semicolon on that entire command, which presses my output. And then let's go to the third column of A, which is going to be the 4 by 1 column vector given by 4 semicolon 2 semicolon 2, semicolon 4. We'll go ahead and suppress the output again. Notice when I ran that, I didn't get any output to show on the actual screen. Let's go over to the fourth column of A, and in this case I'm going to define that by the 4 by 1 column vector 2 semicolon 4 semicolon 0 semicolon 6. We'll go ahead and suppress that output, and then we'll do the fifth column of A, and in this case for the fifth column of A we will not suppress the output. Here the fifth column looks like 14 semicolon negative 2 semicolon 10 semicolon 2. Notice I can check. This is a way to kind of define the matrix step by step. And then I have 2 columns left. Let's go ahead and do the last 2 columns in a bit of a creative way. So we will say that columns 6 through 7 we're going to define as a sub block, and this sub block is going to have entry 2 in the first column, 12 in the second column. We'll go down to the second row. So this is going to be 4 comma 6 semicolon. Third row is going to be negative 1 comma 7, and the fourth row is going to be 8 comma 10. I'll go ahead and leave that open, and notice I've populated that. The right hand side vector B is going to be given by 10 semicolon negative 4 semicolon 10 semicolon negative 6. Now the whole concept that we want to work with is to transform this left hand side matrix and right hand side vector into RREF form, and this is where we actually use augmented matrices. So I'm going to call the function RREF, and then on the inside I'm going to use the little braces, left brace, right brace, and type capital A space B. Spaces in MATLAB and Octave, I can also use a comma in replacement of a space, delineate different entries along the column. So here I have a 4 row by 7 column. When I hit it with a comma or a space, I'm saying, hey, at the end of those columns, append that last column B. And then when I go ahead and run that, let me zoom out a little bit here. Now I get the RREF structure. The first 7 columns of that matrix are going to be the columns of the special form matrix U, and then the 8th column of the RREF augmented matrix is going to be my right hand side vector Y. You might want to pause this video for a second as you transcribe that RREF form. In fact, that's exactly what I've done here. So we've translated AX equal B into an equivalent UX equal Y. Now we're going to use this simplified system to find the complete solution to the original linear systems problem. That complete solution is going to take the form of our template. The complete solution is equal to a particular solution plus all trivial solutions. We make the claim that to find particular solutions, we can use information about the pivots of our matrix U. Remember that the single non-zero entry equal to 1 in RREF form, those columns are going to be pivot columns. The actual scalars that are the pivots, we're going to call those in the pivot positions. So in this case, I have a pivot position in entry 1, 1. I have a separate pivot position in entry 2, 3, and I have a third pivot position in entry 3, 6. The actual values in those pivot positions are going to be known as the pivot. So in this case with RREF, the pivots are always equal to 1. We can use this information to immediately populate the particular solution P. Let me be a little bit more specific on that. Notice that my vector Y literally has non-zeros in entries 1, 2, and 3 in those rows, and that's identical to the very, very sexy looking basis vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. This means if I want to find the values of these x variables that take these columns and send them to that output, I can focus in on the vector y. The vector y is -1, 3, -2. I can decompose that in terms of the orthogonal basis, in terms of the elementary basis vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1, of course with zeros on the bottoms. And then that tells me, hey, I'm going to need -1 of the first pivot, 3 of the second pivot, and -2 of the third pivot, which means the scalar values that I want to put on each of the pivot columns are actually hidden inside the individual coefficients of my vector y. But the goal here is to figure out which linear combinations of the columns of u are going to produce the vector y. Notice I have that information right here. I'm going to need -1 of the first column of y. The second column of y is not a pivot column, and it doesn't show up in that linear combination. The third column of y is the second pivot column, and I need 3 of those. The fourth column of y does not show up. I don't want any of those, nor do I want any of the fifth column. The sixth column of y is a pivot column, and in fact, I need 2 of those in order to generate my vector y on the left-hand side on this case. And then notice the seventh column of y is not a pivot column, and thus I need 0 of it. Let's go ahead and check using our calculator. We're going to go ahead and set p equal to, looks like -1 in the first row, 0 in the second row, 3 semicolon 0 semicolon 0 semicolon -2 semicolon 0. But remember, I actually haven't set the variable u equal to anything. So in this case, u equals RREF of A. And for good measure, why don't I go ahead and say, let's go ahead and take RREF of the augmented matrix. So I'll go ahead and, let me show you this. I said this before, in order to get to previous commands, just push the up arrow. So I'm literally pushing the up arrow, and there's my previous command. And then, do you see how that variable is automatically stored in answer? So I'm going to set y equal to answer, and answer is a matrix, and I want y to be the 8th column of that matrix. So now that's the y vector. Now let's check u times p should be equal to y. It's not always easy to confirm those two things, so what I could do is I could do y minus u times p, and that will be, that should be, if u times p is equal to y, that should be 0. It's also not easy per se to check something as 0 by checking individual entries. Sometimes that's a problem. So instead what we could do is we could actually take the magnitude of y minus u times p. If those two things are equal, we expect that value to be exactly equal to 0, or in a computer, very, very close to 0. And you see, hey, the magnitude of that vector is 0. We know from definition of the norm, the only vector that has a 0 norm is the 0 vector. So that means y minus u times p is 0, which means u times p is equal to y. With that, we've just found the best looking particular solution that we can find, the one that depends only on the pivot columns with 0 information coming from the non-pivot columns. The next question that we have is, how do we find trivial solutions? Recall that in order to find trivial solutions z, any trivial solution, we're going to focus on finding what we called special solutions to the homogeneous linear system problem involving the coefficient matrix U. We also recall that each non-pivot column leads to a unique special solution. Later in the videos for these lessons, we're going to talk about what we mean by the word unique, aka linearly independent. For now though, let's go back and do some little bit of recall. When we look at the RREF associated with the matrix A, we see that our 4x7 RREF structure yields 3 pivot columns, 1, 2, 3, and then 4 non-pivot columns. We recall from our last video that every column is either a pivot column or a non-pivot column. In other words, the number of columns is equal to the number of pivot columns plus the number of non-pivot columns. For this specific example, that implies that 7 is equal to 3 plus 4. Because we have 4 non-pivot columns for the matrix in this example, we're going to say we expect 4 unique, separate, special trivial solutions to the homogeneous linear systems problem involving the matrix U. Another way to say this is we expect 4 separate z values, u times z1 equals 0, u times z2 equals 0, u times z3 equals 0, and u times z4 equals 0, each of which is associated with information encoded in the non-pivot columns. This implies that the best way to find these unique, special, trivial solutions is to really focus in on those non-pivot columns. This is because each non-pivot column gives rise to one unique special solution. There are 1, 2, 3, 4 non-pivot columns, so we are looking for 1, 2, 3, 4 unique special solutions. Let's find them. We'll start our search with non-pivot column 1. We're going to use non-pivot column 1 to find the first unique special trivial solution. To do this, we can write out non-pivot column 1, which is the second column of our matrix, -1, half, 0, 0, 0. Well, that is a linear combination of the previous pivot column. That's -1 half times 1, 0, 0, 0, which is -1 half times column 1, the first pivot column of my matrix. Doing a little bit of algebra, I can bring the right-hand side over to the left-hand side, and I see the linear combination 1 half times column 1 plus 1 times column 2 equals 0. 0 is what I'm searching for on the right-hand side, and in the actual vector z1, I want to know how many scalars of each individual column of u do I need to produce that 0. Well, in this case, it looks like I'm calling out 1 half times the first column, 1 times the second column, and then this linear combination involves no other columns of u, so we put zeros all the way down. Here we can check this work in Octave. We go ahead and set z equal to 0.5, 1, and then in this case we're going to go ahead and define 5 by 1 zeros all the way down. That's a function. So now I get that vector. And then what I want to know, if I multiply u times z1, what do I get? Well, lo and behold, I get zeros. We said in the last video, on the example 1 at least, that when I multiply a times z1, I should also get 0. Looking back at the second non-pivot column of u, I see that that non-pivot column is 1, 1, 0, 0. That's going to be a linear combination of the first two pivot columns. Specifically, the fourth column of my matrix U is going to be 1 times the first column plus 1 times the third column. I want to get one side equal to 0. In this case, I always like my scalar for the new non-pivot column to be 1. So I'm going to bring these coefficients over to the other side and they turn negative. Now I have this linear relation, -1 times the first column plus -1 times the third column plus 1 times the fourth column equals 0. When I'm populating this vector, I have -1 of the first, 0 of the second, -1 of the third, and 1 of the fourth, and the rest of these get 0. And we can, of course, check this work in Octave or MATLAB. All of the code that we do in Octave is identical to code that we're doing in MATLAB. Thus, when you learn how to code in Octave, you get free lessons in MATLAB as well. It's one of the reasons that I chose this. When I go ahead and multiply u times z2, I get 0. A times z2, I also get 0. Notice we have a bit of a pattern. Look, the special solution associated with pivot column 2 takes the entry in that pivot column, turns it to a positive, and then leaves the 1 alone because I need +1/2 plus 1 of those to get to 0. Over here, the entries in the first two rows of non-pivot column 2, each of those entries turn to a negative, get placed in the corresponding column index for the pivots, and then the fourth entry associated with non-pivot column 2 stays 1. Could you guess what we're going to do to find the next special entry? I can. We're going to take positive, that negative turns to positive, puts it in the first pivot. I don't have any of the second column because it's a non-pivot. Third column, positive turns to negative, gets that number. I don't have any of the fourth column because it's a non-pivot. And then I'll go ahead and just take 1 of the fifth column and 0 of the last 2. And to get the fourth special trivial solution to this, we'll go to the fourth non-pivot column. Here, I'm going to turn the positive to a negative, put it in pivot position 1. I have 0 of that non-pivot column. Positive turns to negative, put it in pivot position 2. So pivot position 2 is in column 3. That's why it is in row 3. I'm going to take none of the second non-pivot column, none of the third non-pivot column. Here, negative turns to positive, so that's a 1 in the third pivot position. The third pivot column is in column 6. That's why that entry goes into row 6. And then finally, I just want a 1 on that last one. Here I've made some conjectures without formal reasoning. I'm going to check those conjectures using my calculator. 3 semicolon 0 semicolon negative 2 semicolon 0 semicolon 1 semicolon 0 0. And then my z4 vector is going to be negative 1 semicolon 0 semicolon negative 4 semicolon 0 semicolon 0 1 semicolon 1. Let's go ahead and check u times z3. And we also see that a times z3 is equal to 0. U times z4, and that also means a times z4 is equal to 0. Now, for good form, let's confirm analytically the same information that we just conjectured by doing pattern recognition. Using pen and paper analysis, we see that the fifth column of u, my third non-pivot column, is negative 3, 2, 0, 0, which is negative 3 times the first pivot, 1, 0, 0, 0, plus 2 times the second pivot, 0, 1, 0, 0. When I'm doing this linear combination, I'm going to bring these over to the other side. So the negative turns to positive. I have 3 times column 1, 0 times column 2. Positive turns to negative, negative 2 times column 3. 0 times column 4, because 4 is a non-pivot column. 1 times column 5, and then 0, 0. I tend to like the scalars associated with the indices for each of my non-pivots to be positive. Of course, you could have brought this over to the other side and kept those negative 3, 0, positive 2, 0, negative 1, 0, 0. And in fact, any linear combination, any scalar multiple times this vector will work. So I could have multiplied that by 2. This could be 6, 0, negative 4, 0, 2, 0, 0. Go ahead and check that in your calculator. Any scalar multiples of these will work. I tend to choose the one that is a unique linear combination of the pivot columns and places a positive 1 value in the index associated with that non-pivot column in the original matrix. We go ahead and confirm the last one as well. I want a 1 in the 7th. I know I'm going to want a negative 1 because I'm going to bring it over to the other side to get 0 in the first pivot column. Second column is a non-pivot. Third column is going to get negative 4th. Fourth and fifth columns are both non-pivots. Sixth column is a pivot. There's a negative. I'm going to bring it over to the other side. It becomes positive. And indeed, I've now done analytically, aka paper and pencil, what I confirmed by a conjecture and calculator. Remember, the whole goal of all this work, we have found the particular solution and we're looking to find trivial solutions. We're making a claim that any trivial solution is going to be written as a linear combination of the special trivial solutions, the unique ones associated with the non-pivot columns of my matrix. For this specific example, that means if I'm looking to write what that trivial solution should look like for any possible case, I'm going to say that any trivial solution is going to be written as a linear combination of the special trivial solutions. Another way to say that is that Z is C1 times Z1 plus C2 times Z2 plus C3 times Z3 plus C4 times Z4, where these C's can be anything under the sun. We've just done a ton of work in this example, and we're actually going to take a break here and move on to the next video so that this video is not 45 minutes long. Before we do that, though, I want to remark, these individual vectors come from focusing on the non-pivot columns, and non-pivot column 1 was column 2 of my original matrix. Non-pivot column 2 was column 4. Non-pivot column 3 was column 5, and non-pivot column 4 was column 7. Making the direct translation between the column index in my original matrix and the corresponding count of those columns in the enumeration of non-pivots is going to be important when we start to define what we call pivot variables and free variables. That's exactly what we're going to do in the next video.